Hey, welcome to Exponential Equations and Introducing Logarithms. We've done a lot with the exponential function. Here's one here, and here's another one here. And I've drawn the graph here with the Casio for both of these. And I guess you can see there's our new friend E. And we need to get excited about how important he is for later on in modelling particularly population growth. But the question arises now, if we wanted to take this exponential function here and find out when the amount would reach, let's say 200, let's say it's in grams of bacteria or something, we want to know up here, when do we reach that y value of 200? What's the x here, which is time t in our context, but with technology it would be y and x, wouldn't it? And how would we do that? You say, hey, that's easy. I'll just go to Shift F5 on the Casio and G-solve it, mate. Oh, G-solve it for an X-calc. Do an X-calc for a Y equal to 200. I'm going to ask the calculator to solve this problem for me. And sure, that's okay. And you can do that. But hey, you're a budding young mathematician. Don't you question, like, how would you do that mathematically? How can you get the calculator to do it? What's the math behind that? So I made some up down here. 200 equals that. Could we solve it? I'll give you a hint. We're going to need to later on divide both sides by 100 to get back to an exponential. But look at all these. We're going to try and find when 100 grams grows to 200, 400, 800, 1600, for example. That's going to be exciting. So let's have a look at the basic skills required to do simple exponential equations. So come down here now, and I've used clippings from Hayes and Harris this time. You don't need that textbook with you because I've just used part of it. But let's have a look at very, very simple exponential equations. 2 to the x equals 16. What are we going to try and do? Well, we want to try and write both sides as a power of the same base. Base 2 is obviously here, is obviously to be used here because 16 is 2 to the 4th. Then we say, well, hang on, we've got both sides are powers of 2, and the sides are equal, therefore the powers must be equal. X must be 4. What about something harder over here? 3 to the x plus 2 is 1 on 27. Can you write 27 as a power of 3 because the other side's written as a power of 3? Oh yeah, 27 is 3 cubed. So 1 on 3 cubed is 3 to the negative 3, and so x plus 2 must equal negative 3. The two sides are equal, the bases are the same, therefore you can equate the powers. And subtracting 2 from both sides, x is negative 5. Alright, so can you see a crucial step is write both sides, or write this down here, both sides as a power of the same base. That's what we're going to do in each of our problems later on, and we're going to do it in all of them. We're going to develop some techniques including use of logarithms, but that's the same notion. And then once we have the same base, this little dude here is saying we then equate the indices or powers. Alright, so can you have a go at these? The answers are over here. Now check your answers as you go so you don't perpetuate a silly error, silly mistake. I want you to pause the presentation now and have a go. Alright, coming back, we're going to go on to some a little bit harder looking. Let's have 4 to the x equals 8. Can you see why it's different? It's not obvious on how to write both of these as powers of 4. Well, one's a power of 4 already, but 8, well, maybe we should change to writing them to some other more friendly common base, because 4 is 2 squared. And 8 is 2 cubed, that's easy. And now we've got to know our power rules. 2 squared to the x, hang on, that's a to the m, all to the n. You've got to multiply those powers together. So the top power now is 2x, and the bases are the same, so the powers must be the same. So you equate the powers or indices, then divide by 2. What about this critter over here? 9 is 3 squared. And a third is 3 to the neg 1. Now, look out, we have a power raised to a power. Come over here, you've got to multiply those powers together. Look at the bracket, it's going to be 2x take 4. Don't forget to double the 2 in there. These are the 2 powers. Must multiply them carefully, and then we'll equate the 2 powers and solve the equation. Adding 4, neg 1 plus 4 is 3, and then dividing by 2. Alright, so got some more problems down here from Hayes and Harris, and I've also put in now the ones we had before because you're ready to do them now. I would like you to divide both sides by these hundreds first. Divide both sides by 100 to get the basic exponential equation, which is the base raised to the unknown or variable in the exponent on a side by itself. So remove the 100 first of all by dividing both sides by 100. Okay, so all the answers are here. Check as you go. I think you should do most of these to get your skill level up. And here are the answers to the added few I put down the bottom, because this is a thread we're going to work through as we develop our exponential equation methods and skills. Okay, so pause the presentation now and have a go. As I said, try to do all of them. All right, moving on, I guess you would be asking now, how would I do something like this? Have you realised that when we divided by 100, over on this side, in all those previous ones, we've always been able to get something that you can write as a power of the same base. We can't write 8.5 as a power of 2. Okay, not easily. So how are we going to do it? Well, maybe we'll choose another base for both sides, like we were playing with up in the last set. So, our number system is a decimal system. It's base 10. So what about choosing powers of 10 for both sides? And that's what we're going to do. So we're going to come into an area of mathematics called logarithms. The logarithm of a number is the power of the base. So a logarithm is the power of the base required to produce the number. So that's the idea, and that's where we're going to introduce it. Required to produce the number. And we're going to use base 10. And on your calculator is tabulated or stored all the numbers as powers of 10. And so that's where logarithms comes in. It helps us solve these exponential equations where we need to write both sides as a power of the same base, but that power isn't obvious and it's not easy to do. Okay, let's go and look on the calculator now. And I've done something from the Casio here. Can you find it? Here it is in here. LOG means base 10 is being used as the base of your logarithm. So we're going to write each number as a power of 10. So that's called the log of the number. Log of 8.5. This is the power of 10 needed to get 8.5. So in other words, 10 to the 0.92941, etc. will give the number 8.5. Okay, and actually then you can go on and work out the log of 2 and so on. So that's what we're going to do in this little section. Now let's have a look then at doing that with our problem. Here's our problem. So let's divide both sides by 100, as we said. 8.5 is 2 to the t on 25. Now the log of 8.5 was 0.9194, so we can call that 10 to the 0.9194 equals, a log of 2 was 0.3010, all raised to the t on 25. So now the bases are the same. We use logs to get the powers here. So now the powers must be the same. And we're going to over here have to multiply those two together. It's 0.3010 times t on 25. Okay, so now can you see we can do it? Let's divide both sides by the log of 2, or that power of 2. And if we do that, we get 3.0875 on your calculator. And now we can multiply both sides by 25 and get our t value. And if we do that, we will have 77.2 in minutes or hours, whatever it was, we didn't specify that, to 3 significant figures. Now, wasn't that good, but it looks very clumsy up here. So what we tend to do is do it all in logland. So we say the log of 8.5, so we're going to depower it straight away, equals the log of 2 to the t on 25. So we're going to leave out all these clumsy powers of 10 here. And now we're going to say log of 8.5 is t on 25 times the log of 2. We're just doing it in powers. We're just mentioning how we can do this in powers. So we're going to go straight to this step. Find the log of the left hand and the right hand side. And if it's a number raised to a power, it'll be the power times the log of the number. Why? Because there are 2 powers here. When you find the log of 2, you're working with a power of 10. And then we would come into this line and divide by log of 2. So that's our log notation. But what's happening over here is we're really encoding it as powers of 10. We're just not going to go through the 10 to the expression all the time. Let's come down and have a look at this one here. Same idea. Oh, we got e in here. So what will we do? Try to isolate this term first by dividing both sides by 50. So we get 4 equals e to the 2t. Now, we could take the log of both sides here, but because e is equivalent to the exponential function, or the natural number e, because it seems to occur naturally in so many things in our world. We'll see that later on. So natural number e, we could actually use logarithms to the base e, because if we took a log to the base e of this side, the answer would be just 2t, wouldn't it? What power do you raise e to get this thing? It's just the power, it's just 2t. So we do have defined logarithms to base e. In other words, we're going to write every number, so this implies every number can be written as a power of e. And that's going to be helpful if we have lots of e expressions. Because can you see it up here? Can you see it? If you use a base e on that side, the log of it is apparent. The log is the power you raise the base to. So the power just comes straight down. So we need to then find log to the base e of 4. Well, the abbreviation for log to the base e is ln, meaning natural n for natural log. Natural logs. Because we're saying e is the most naturally occurring base for exponential functions. It's called the exponential function or the natural number e. So when we try to write all other numbers as powers of e, we try to write the natural log, ln, of 4. So that will save us time rather than finding log to the base 10 of e and then multiplying by 2t. So that's another log. Is it on your calculator? It certainly is. And this is the one we'll be using most. So let's come in here, have a look in here, ln, that button there that had e to the x at the top of it. And that button will find the log to the base e of any number. So if you push ln 4, you'll find this is the power of e to get 4, e to 1.386,294, etc. will give the number 4. That's going to help us in those exponential equations where e is the base. All right, let's come down and have a look at this question that we had. We'll just put it there. Dividing both sides by 50 again, isolating the exponential term there, and then taking the log of both sides. Log of 4, the power I raise e2 to get 4. What's the power I'm raising e2 to get this? It's just the power. It's already written as a power of e. So it's easy to find its power or its log. Therefore, dividing both sides by 2, ln 4 on 2 would be our t, and if you do that on the calculator, as we saw above, it's 1.38629, etc., divided by 2, and then it would be, t would be 0.693 to 3 significant figures. Just a little note here, of course we work with at least 4 figures if we want to round the final answer to 3. We don't keep rounding throughout a problem because we'd lose accuracy all the way through. So do you get it? It's the same idea as our simple exponential equations, only we're choosing a different base, either base 10, or if e is in the problem, the obvious way to find the log is to use base e. All right, let's come down and have a look at what Pearson's have got. They've got a number of examples. So I'm taking screen clippings from Pearson's. It would be handy to have the book there with you. So here's the first one that they're doing, and I think we've just done one like that. The log of 2 is the log of this side. Log to the natural base e means, hey, this side is already written as a power of e. So its log, the ln, is just the power. And so you can easily solve for it because it comes straight down and it says the power of that side must equal the power of that side. And that's what ln2 is, isn't it? This is the power of e to get 2. So it's the same idea as our little ones. So in here, ln2, we're saying, well, we're writing 2 as a power. Here's its power. The powers must be equal on either side, and then we divide. Okay, so here that would be equivalent to a continuous compounding interest rate of 7.5%. That's another cross-link with what we did before. Okay, so let's go down. They've got a property here, log to the base b of b to the x. We haven't done that definition. We're going to do logarithms as a separate mathematical function later on. I wanted you to see the reason for finding it, discovering about logs, is actually rooted in solving equations, exponential equations. Let's have a look at another one now. Here's example 17. 3 to the x take 4 equals 24. No, we could use ln, natural logs, because you can write both of those as a power of e, but we usually only use ln for equations where e is the base, for equations e as the base in our exponential function. So here, let's go back to log to the base 10. So we're going to find, when we put that log, we're going to find the power of 10 for both sides. And if we're going to find a power of 10 for this, we have to multiply that power of 10. There it is. Log of 3 is a power of 10 to get 3. So we must multiply it by x take 4, because what effectively we're doing, hang on, I won't put a, I'll put 10 there. We're finding a power of 10 and then raising it to another power here. Okay, where this other power is x take 4. All we're doing when we write that word log is saying I'm powering it up as a power of 10, and I'm powering this side up as a power of 10 as well. So then I can divide the logs and add 4, and they've done it all as one step on the calculator, which is probably preferable. Okay, so coming down, let's have a look at another example. Here we have 1,000 euros, so we just skip back. Compound at 6% quarterly. How long would it take to get 2,000 euros? So here, what we're saying is it starts with 1,000 and it goes to 2,000, so that's doubling. So they put P in there. I would have preferred they put 1,000 and 2,000 and then just divide both sides by 1,000 and get 2 equals that. Same process, isolate the exponential term. Just check that term though. It's 6% per annum, 4 times a year, and then if that's the number of years t, this will be the number of calcs, the number of calculations we do at this multiplier in here. Alright, so there we have simplified our exponential equation. Now we want to write both sides as a power of the same base. So now we might use ln. It doesn't really matter what you use here. Could be base 10. So ln of both sides means we're writing both sides as a power of e. So if we write 1.015 as a power of e, and that's what's suggested by ln, then it will be 40 times that power of e. Just remember, effectively when we're using logs like this, we're needing to multiply the log by that other power, because it's really a power raised to a power here. And so ln2, and then into the division again, we'll divide by this, and we've got to divide by the 4 to isolate the t. You can do it in 2 stages or 1 there. Are you getting the hang of it? Let's keep going. A couple more examples here. If you have got strep throat, the bacteria that cause strep throat are called streptococcus. Streptococcus. And coccus means it's a round bacterium, round shape. And so they grow at about 2.3% per minute. To the nearest whole minute, how long will it take for them to double? So let's set up the equation here. So Pearson's talks about it here. There's our basic starting point. What is the multiplier here? What's happening in B? Well, every how long does it go? 2.3%. They talk about some simple interest and stuff there. I want to just go straight to the bacteria multiplying and say, well, we'll have all that we had before plus a growth of 0.023. So that's our multiplier. Similar to an interest rate, a 2.3% interest increasing. So coming down here, we've got this, and we're saying how long will it take to actually double here? We want to double the original. So we have the exponential equation is how long would it take to, and just go back up again here. We slip down a bit. So how long would it take to get to that point? We're getting a lot of slips here. So we've got this expression here then, and we want to find the time for that. So we'll take the log of both sides, and then we're raising it to the power. So that's the t power times the power of e. And you could do, mind you, with log. Could do log here. That's base 10. If you wanted to, you get the same answer. All the numbers will be different powers of base 10. The process is the same. And then dividing, we would have it 30.482. This was doubling every minute if you go back to the beginning of the problem. Rate of 2.3%, sorry, 2.3% was the growth rate per minute. So t here was in minutes. All right, let's go and do another one. It's getting a bit repetitive now. And back to compound interest, investing $1,000 How long will it take to get to 4,000 10% compounded monthly? So what we're saying is, there's our 1,000, here's our multiplier, 10% per annum, divided into 12 equal months. How many months in this many years? 12t, so we'll be in months now. And here's our only difference. We're asking for it to be an equation. When will our exponential function grow to 4,000? So the first thing to do, divide both sides by 1,000 and cannot come up with that equation. Fine, and they've gone back to base E now, base 10. Write 4 as a power of 10. Write 1.0083 as a power of 10. And then you'll have to multiply that power of 10 by 12. So the log of 4, this is all in power land now, powers of 10. And you've got the power of 10 for the other side, and you must multiply by 12t, because what you're effectively doing is making 1 a power of 10, and then what it's raised to will have to be multiplied by that power. So the power nicely comes down so that you can solve for it. It's not sitting up in that power line. Then dividing by this term, we will have, and by 12, if you want to do it as one step, and it's 13.92 years. So here, I don't know whether that's actually right. I think that's wrong, isn't it? Just looking at that. A minimum number of years needed for the amount. Oh no, that's okay. We've times it by 12 here, so that's good. T is in years because we've multiplied the number of periods by 12. Very good. Can we go down and do another E? I think we're coming to the end now. A 20-gram sample of radioactive iodine decays, so it's given by that. Exponential decay using base E now. This is the one I had at the beginning, and A is measured in grams. Find when it is down to 5 grams. Okay, so here we're working in days here. They haven't said that. Oh yes, here it is, T days. All right, so we want to know when 20 grams diminish to 5. Same thing again, isolate the exponential term by dividing by 20, get 0.25, and then we'll write both sides as a power of E by taking ln. ln is the natural log, which means we're going to use base E, the natural number E. So now, what is the log of this thing? Log to the base E, well, the log to the base E means the power of E. Hang on, the dude's already written as a power of E, so it's easy to take the log of this side, it's just the power. So we have that then, and dividing by 0.087 we get 15.93 days, approximately 16 days to reduce down to 5 grams. So you can see this has added a great dimension to our work, because we can actually solve equations, important equations, if we're going to be able to use our exponential models effectively. All right, come down now and we'll look at the problems. I've split these up into 3 parts, question 1 to 13, so you might pause the presentation now and have a go at a few of those. And down below are the solutions, so I'll slowly go down there now, so you can freeze it later on. It's question 1 to 4. We're fully worked solutions. You could look up the short answers yourself with a textbook. And then we'll go from 5, go down to 5 there, 5 through to 7, 8's a bit longer. So you can pause that. And then we'll just complete 8. Complete 8 there. And then we'll do 9. Let's have a look at 9. Up there, 9 and 10. We'll pause it there to check it. And then going on to 11. 11's a fairly long one. Have a careful look at that. A lot of work in 11. And then into 12. 12, It's got some funny numbers in it as well. Then to 13. Let's see if we can fit 13 in. I think we almost can. Have a look at 13. They're using TVM there. There's the rest of 13. Right, let's look at some more problems. We've got 2 more sets, 14 through 18. Might have a look at those and have a go. Pause the presentation. Let's have a look at the solutions down below here. 14 and 15. Might pause that. And coming down to look at 16 and 17. Let's come down and have a look at 18. That's good. Let's go and have a look at some more problems, the last few now. I'm doing this differently from Pearson's. I'm splitting it into different sections. So you might try and pause the presentation now and have a go at this one, or these 3. And coming down for the solutions, 19. And pause it to have a good look. Hang on, we'll just go back there. 19, have a look. Then we'll have a look at 20. And then finally 21. So you can see you're getting a lot of exciting tools and skills now to be able to handle the models that we have been constructing. And these models are going to be very, very important in applying mathematics to the real world. Lots of exponential growths and decays in models in science, biology, economics and physics. So that's good. Keep up the good work. Try to develop the skills and accumulate them. And I'll catch you in the next presentation, which is going further with logarithms. We've discovered something interesting here. Writing numbers as a power of some base. So we might want to look at this logarithm function in its own right. But until that presentation, it's cheers for now.